Okay, so this month we are talking about chaotic attractors using boost.odeint. This is a library in Boost for numerical integration of ordinary differential equations. And we'll go a little bit into some of the math here, but we're not going to be super drilled down on all the mathematics details. It's well covered in many textbooks and including, and you can get information from Wikipedia and so on. But the motivating use case here is, these chaotic attractors. The Lorenz system is one. This is a series of equations that was created to model weather patterns. You might have heard of this so-called butterfly effect, which is a hallmark of chaotic systems. Another example is the Rossler attractor, and there's also an example from electronic circuits of the van der Pol oscillator. We're going to be taking a look at the Lorenz system and the Rossler attractor in this little talk. So, what is the idea here behind numerical integration? Well, suppose you have some system whose evolving state is shown by this black curve that I've drawn here, and you can't compute the state of the system analytically, meaning it doesn't have a closed form formula. And the idea is that the state of the system evolves over time. So what you're seeing with this black line is the evolution of the state of the system over time as a plot. And in this case, the system is a two-dimensional system, so it has two variables that depend on time only. So the variables don't depend on a third or a second independent variable. They only depend on a single independent variable, that is time. So the state of the system evolves over time, and what that means is as we trace out this curve, that's time evolving, and the black line represents the value of the state of the system as time increases. Now, the idea behind numerical integration as opposed to analytic integration. So analytic integration is where you have a closed form formula for this curve, and you write the formula, and then you integrate the formula over, analytically, so that you can evaluate the system at some other point in time. Now, with numerical integration, the basic idea is that you have at some point on the curve, where my cursor is here, you evaluate the derivative of the curve, and you extend out linearly from the sample point where you know the derivative in the direction of the derivative, and that gives you an approximation to the original curve. And when the curvature, or namely the value of the derivative, is small, meaning that the curve is not changing very tightly, then this approximation is good. You can see that this linear red line is a good approximation for this curve quite a far ways out from the point where we sampled the derivative. Now, when the curve bends tightly, as it does here on this second line segment, we sample the derivative, and then we can't go very far out along this red line before our approximation to the real curve in black is poor. So the error at this point increases rapidly as we go down this red approximation. So that's basically the idea behind numerical integration. We've got some representation of the derivative, which we can evaluate along this curve at any point. We can use the derivative to make a guess and extend out along a linear approximation to the curve using the derivative, and we can measure the error of our guess, and we can do things like take shorter steps along these red line segments if the error is too large, or we can take fixed size steps and then just live with the error that you get. So, like I said, that's just a very, very brief introduction to the idea of numerical integration. As I said, there's entire textbooks that are written about this, and There's not time to go into the huge amount of details on the mathematics, but this is the idea. And the way ODEInt is going to work is you're going to have a data structure that represents the state of your system. And in my little MS Paint sketch there, I showed a two-dimensional system, but it can be three-dimensional, four-dimensional, five-dimensional, 26,000 dimensions. ODEInt doesn't care. And neither does the numerical integration. It doesn't care about the dimensionality of your system. It just cares about being able to evaluate the derivative at a single point so we can compute an approximation to the next value of the state of the system. So ODEInt is a library for solving what are called initial value problems of ordinary differential equations. So an initial value problem means we know the value of the state of the system at some starting point, and we want to perform numerical integration to find out the subsequent state of the system at some further point along in time. Ordinary differential equation just means that the underlying equations depend only on a single variable, which is time in the case that we're going to look at. So here's the motivating it's not really getting any bigger, is it? Here's one motivating example of a chaotic dynamical system. This is the Lorenz attractor, and if we scroll down on this page in Wikipedia, we see here are the differential equations for the x variable, the y variable, and the z variable. And they, in this case, the equations depend on the dependent variables are formulated in terms of each other. They happen to be independent of t, but that's okay. It just means that the variables themselves are coupled together, but they're not directly coupled to t. It doesn't mean we can't formulate the state of the system using that variable t. It just means that we start the system at some initial state, and whether t is 0 or 10,000 doesn't make any difference. As we evolve the state of the system, it will continue to evolve in the same way for the same initial conditions. Now, what makes the Lorenz attractor a chaotic attractor is that if I take the same set of equations for the Lorenz attractor, and I start at two different initial conditions, and I evolve their trajectories over time, then even though the initial conditions can have the state being very close to each other, as I evolve each of those two different initial conditions separately, they will eventually become arbitrarily far apart. And that's the so-called sensitivity to initial conditions that a chaotic system demonstrates, whereas there are other systems of coupled equations that don't have that characteristic. So if we take two initial conditions that are close together and we evolve the state of the system for those two different initial conditions, if the initial states are close together, then the trajectories will stay close together as we evolve the state of the system. I haven't mentioned what an attractor is. The idea of an attractor is, as I evolve the system, maybe the system converges to a single state. So I run the state of the system forward, and then it just hits a certain value, and then it just stays there. That's a so-called fixed point attractor. There's also the idea of there being an attractor at infinity, where I evolve the system, and points that are attracted to infinity, the magnitude of the state just gets larger and larger and larger and grows without bounds. In the case of the Lorenz attractor, there's basically two lobes here in three-dimensional space, and the system will evolve alternately oscillating around the two one of the two lobes. It won't grow unbounded, and it won't go to a fixed point. It just keeps oscillating back and forth between these two regions in space. And similarly, the Rossler attractor, which here's the equations down here for the Rossler attractor. And again, it doesn't depend directly on t. The equations just are, for the three variables, reference each other, but not t. The Rossler attractor has a region in the plane, and then it has a region tilted up out of the plane, and the system kind of continues to evolve in this region and stays bounded, doesn't converge to a single point, so it doesn't converge to a fixed point. It stays bounded, so it doesn't diverge to infinity, but it oscillates around in this region and does not converge to, a periodic path or a single point. So it also exhibits the sensitivity to initial conditions. So that's basically the idea behind these chaotic attractors. They can create interesting pictures, and that's what we're going to do in a very simplistic way using this library. So this is a header-only library, and the documentation is good. I found only one problem, which is that the CUDA examples have kind of rotted away a little bit. I was not able to make the CUDA examples build for me. I've let the maintainers of the library know, so maybe they can get those examples updated at some point. However, I was able to build several different examples from the repository. I did find a few little just minor errors. For instance, one of the examples assumed that the iterator over a container was implicitly convertible to a pointer to an element in the container. That's not necessarily true. For like std array, that's not necessarily true. So just some minor adjustments to some expressions took care of those problems. In my example code here, I've got my own example that I wrote, which is going to visualize the Rossler attractor and the Lorenz attractor using OpenGL. It's a very simplistic visualization, but you'll see that it looks similar to these pictures in Wikipedia. And I've also I've got the boost.odeint library as a submodule in my repository, and I've built a couple examples out of the repository, and the ones that needed minor modifications, I've just copied the examples into my repository and made the modifications there. So you can get an idea of how that looks. But one of the interesting things about this library is, as I said, there's been many large textbooks written about numerical integration. It's a well-studied topic. There are lots of different considerations based on the characteristics of the system of equations that you are attempting to integrate. And being a header-only library, ODEInt attacks that ecosystem of problems by providing template functions and template. I believe it's all template functions, where the template arguments model specific concepts. And the idea is that as the concepts become more refined to talk about specific characteristics of your equations or the algorithm, then different implementations are substituted to give you the best. Now, best here is in quotes. The idea of a suitable, appropriate algorithm for the situation. It sounds kind of vague, but as we'll see in my example code when we look at that, there is, and we saw it in that little MS Paint sketch, right? There's points where you're going to do this guess off of the derivative, and the error is going to be large. Maybe that's not acceptable. So there is a category of algorithms that what they do is that when the error exceeds your acceptable limit, they choose smaller steps along those red lines, the approximating lines, so that when the curve is bending tightly, we're taking smaller steps, and therefore our approximations stay within our error bounds because we're not moving too far along the curve before we take the next evaluation. And I have implemented some time ago an example of one of these numerical integration algorithms with so-called adaptive step size, where you're looking at the error for all of your guesses. You're looking at the error, and if the error is too large, then you reduce the amount of you reduce the step size along the curve to get a closer refinement. And that what that means is that the resulting points that represent the state of the system, they're not evenly distributed in the independent variable time. And these are time-varying systems that we're talking about here. So when the system is low curvature, we can take very large time steps. Say we're integrating from 0 seconds to 10 seconds, we might be able to take a time step of 1 second where the system is very flat. Where the system curves tightly, we have to take smaller time steps. So we might be taking like 0.01 or 0.005 as our time step, and therefore we get the state of the system, but it is not uniformly sampled in time, if you know what I'm saying. There's also this concept of a stiff system. We're not going to go into the details of a stiff system. That has a very precise mathematical meaning, and if you're working with your own formulas that you're deriving from a physical system that you're trying to simulate, you'll know if your system is stiff or not, and if not, you'll consult mathematical textbooks that'll tell you what constitutes a stiff system to find out if your system is stiff. And a stiff system has additional work that has to happen in order to integrate it numerically without error. So let's take a look at a couple of their examples here. Their first example in the documentation. The documentation, by the way, is just fine, but it assumes that you understand the mathematical terms involved with ordinary differential equations, initial value problems, what does it mean for us to call a system a stiff system, and so on. So if the mathematics is putting you off, I don't know how to, if the mathematics is a problem for you, I don't know how you're going to get around that, because you're doing a mathematical algorithm here, and you have to understand the underlying mathematics in the sense of at least the concepts that are involved. You don't necessarily need to understand every single step in the implementation of these algorithms, but you will need to understand your mathematics enough to be able to select the appropriate algorithm for your use case. So inside here, they've got what's called a harmonic oscillator. And in all their examples here, they're going to refer to something that's called the state type. So this is the data structure that holds the state of the system. So in a system of two equations, the state of the system is determined by the value of the two variables. So they've got, in this case, a vector of double as the data structure holding their state. Now, typically, you will supply to the library either a class with a function call operator or a plain old function that accepts the current state of the system, which does not change. So here, that's why this x variable here is taken by const reference. You're going to compute the value of the derivative at a time t. So that's why the state type reference dx dt, this is the derivative that we're going to compute. And the value of t at which to compute the derivative. Now, in this case of this harmonic oscillator, the harmonic oscillator doesn't depend directly on t like the Lorenz attractor and the Rossler attractor. So the t argument here is needs to be there for the function signature, but it's commented out. And so following the equations for a harmonic oscillator, they're computing the derivative. So the derivative of the first variable is the value of the second variable. The derivative of the second variable is a combination of the first and second variables using this gamma constant. So the idea being many of these systems of equations have these parameters that define the specific instance of the system in terms of some kind of parameter. So oftentimes, things like physical systems that have masses and springs, there's a spring constant that's it doesn't change the differential equations, but the value of the constant determines the behavior of the system. So in this case, this harmonic oscillator is characterized by this gamma constant. Now, this is an example where they've written the derivative of the system as a plane function. Here they've just recast it so that, this was for a fixed gamma, and here they've got a harmonic oscillator that can be configured for a particular gamma, and they're holding the gamma constant as a member of this class, and then the function call operator is computing the same equations. It's just using the gamma constant from a member of the class. So they can define different examples of the harmonic oscillator for different gammas. Now, in order to do this numerical integration, we're going to need to take steps, and that's this concept of the stepper that they have here. So you're going to make some step dt from the current state to compute the new state at x of t plus dt. So that's what they're saying here. We've got the current state at x of t. We're going to take a time step dt to get an approximate value for the state of the system at t plus dt. And the simplest thing to do is to use a constant step size, which is an example. Here they're using a so-called Runge-Kutta stepper, and they're going to integrate using that stepper and the harmonic oscillator function that computes the derivative. This is the current state of the system. This is the starting value for t. This is the ending value for t, and this is the step size to use. So going from 0 to 10 in t in steps of 0.01. Using this Runge-Kutta 4. Runge-Kutta is a very well-known numerical integration algorithm. The 4 is because it's fourth order Runge-Kutta. And again, you can look up these algorithms, and if we go over here to Wikipedia and we say if I could type Runge-Kutta methods, and we see here, here's the function evaluations that are taking place, and there's 4 of them. That's why it's called fourth order RK4 approximation of y of t of n plus 1 and the next value y of n plus 1 determined by the present value of y n plus a weighted average of 4 increments. So that's what you can see here in this diagram, what they're doing. It's evaluating the function 4 times and then computing a weighted average of them in order to we need to go back to, we're going back to here. So that RK4 is just very, very commonly used numerical integration method. And again, if you want to use a specific numeric integration algorithm, there are choices inside boost.odeint. If you don't make specific choices, there are defaults given. So even if you don't want to mess with understanding, like should I use Runge-Kutta 4 or should I use this Runge-Kutta Cache Carp 54? This is an adaptive step size. You can do straightforward things and get some results. to get the best results, you will want to tailor the stepper and the state of your system. You want to tailor the stepper that you use for the use case that you have. And we'll see how this manifests itself when we look at my example in a little bit here. And I'm not going to go through every single bit of the examples here, but they show you how to, use different variations of Runge-Kutta to get control over the amount of acceptable error in the approximation. And this is numerical integration. It's not analytic integration, meaning we're not computing the value of the state of the system directly from formulas. We are numerically integrating to get an approximate value of the state of the system. And all these approximations, they have trade-offs. The different algorithms have different trade-offs between the amount of error that they produce and the amount of computation necessary to get the value. Maybe you need to compute the new state of the system quickly, and so you're willing to accept more error, or maybe all you care about is fixed step size. That's the important thing for you, so you don't care about the error that's introduced when you take large steps, when the system is changing rapidly. Those are all choices that you get to make with this library. Now, coming back up here, I recommend reading through these different examples that they have in their tutorial. We'll look at a couple in a second here as code. One of the things that makes this library flexible is that we saw in that one example for the harmonic oscillator here that the state type was a vector of double, but it could also be a stood array of double, or it could be an indexable type from some other library. It could be your own data structure and whatnot. The main constraint is that this, like for instance, this is a template function and it's templatized on the types of the arguments. So as long as the arguments are used, as long as the types of the arguments are used in a consistent manner by the, this is a template function, or rather, this is not a template function. This is a function on specific types, but the integrate functions are template functions, and as long as the types of the arguments passed to the integrate functions are consistent with the semantics and expressions used inside those integrate functions, then you can use any type that's compatible with that. Now, that's just a fancy way of saying you can use like stood array, or you can use stood vector, you can use your own data structure, you can use data structures from third-party libraries, and as long as they can be used consistently with the expressions in these algorithms, everything will work just fine. And the details of that are explained here in their concepts section, where they describe the concept of the system, the concept of a second-order system, a symplectic system, an implicit system, the concept of a stepper or an error stepper, a controlled stepper. The difference between like a stepper and an error stepper is what allows you to take adaptive step sizes. Now, let's take a look at some code, because we've just kind of been talking very abstractly so far. So if we, the way I've arranged this examples here, these are examples from the Boost library itself. And then down here I've got my little GUI program that's going to do the Lorenz attractor and the Rossler attractor that I've implemented inside my code. So let's do, they're kind of increasing in number here in complexity. So if we take a look at their example here, so this is the whole program. As I said, it's a header-only library, so just include boost. It's in the subdirectory numeric odeint, and they're doing a using namespace here just to bring all those identifiers into scope without having to qualifying them with a full namespace. Here's their system for the Lorenz equations. The Lorenz equations are characterized by three constants, a sigma, a rho, and a beta. If we go back and look over here at Lorenz in Wikipedia, you see here's the rho. Sorry, that's a sigma. Here's the rho, and here's the beta. So the constants sigma, rho, and beta are parameters representing physical properties of the system. And instead of writing out rho, they wrote out R. Instead of writing out beta, they wrote B. And we can see that for Lorenz's original experiments, he used a value of sigma equals 10. So sigma equals 10. Rho equals 28. Rho is 28. And a beta of 8/3. So a beta of 8/3. So this is exactly the system that's described in Wikipedia. And this formulation of the derivative, it's massaged around a little bit compared to the Wikipedia formula, but if we look at it carefully, we can see that it's written the same way. So for the first variable, the derivative is sigma times the second variable minus the first variable. So the derivative of the first variable is sigma. Let's make this a little bigger. Sigma times the second variable minus the first variable. And we've represented the state of the system as a stood array of three doubles. So that's why we're using indexing here instead of saying state.x, state.y, etc. And this formula, it looks a little different, but it is identical to this formula from the Wikipedia formulation. And then again, they've kind of just swapped the terms around a little bit for the third formula, but so this is matching exactly the formulas on Wikipedia for the three derivatives. And here they've just written a little function to write out the state at a time t. And this is the initial conditions. So we remember when we call this integrate function, we're going to pass it the functor or the function that computes the derivative, the initial state, the starting time value, the ending time value, the delta t increment between steps. We're taking fixed size steps with this integrate algorithm. And there's an overload of this algorithm that lets you supply a function that will be called every time a new state value is produced. And in this example, it's just a function that writes the new state out to standard output. So if we run this, oh, I've got a breakpoint here. Let's just step into it so we can see what the code looks like down in the library. You can see that, as I said, these are all template functions. So the type of the observer, the type of the time variable, the type of the state of the system, and the type that represents the system itself, namely the thing that computes the derivative, are all template arguments to this function. And this little enable if here is just selecting a particular overload for the proper use case. And here they're saying they're going to use the Runge-Kutta Dupri 5 stepper, and that's going to be, this stepper is nested inside a controlled Runge-Kutta stepper, and that is the stepper type that they're going to use for integrate adaptive. So that type is instantiated, so that gives an instance of the stepper to this integrate adaptive algorithm, and all the other arguments are just forwarded on. If we step into, this is the constructor for the Dupri 5 stepper. We'll step out of that, step in again, Here's the default step adjuster, which must be what the controlled runga kutta. It must be a. Let's find out if this is my theory is correct. It looks to me like it goes into there's this default step adjuster, so maybe it's an argument into that. Let's find out. We'll step in again. Here's the default error checker, and here's controlled runga kutta. So now we have an instance of our stepper that's passed in here. This stepper variable is now an instance of that big template specialization that we got. And then it's going into a detail function, having computed it's going to build a stepper category. And then we get into integrate adaptive again, and here's our little loop. It's going to call the observer. So it calls the observer first because you want the initial state to be noticed by the observer, not just any new state. And now we're going to try a step, possibly failed, keep doing a step, and now that was try step because it was making adaptive steps. So it was adjusting its step size to find one that satisfied error criteria. And so now we've incremented our little counter, and now we're calling the observer on the next state. And if we go back here to our little console output window, we see here was the initial state, 0, 10, 1, and 1. And if we go back to the Lorenz system, initial conditions, I don't think you have to start at a specific initial condition. So 0, 10, and 1, at time 0, initial state 10, 1, and 1 is fine. And if we step out of this whole thing and step out, so now that whole integrate process has completed. It integrated from time equals 0. Let's go back up here to the top of this window. From time equals 0, and you'll notice that these increments in time are not uniform. It depends on how tightly curving the system was at any given point. Here we went from 0 to 007, and then went to 017, and then went to 028, and then 040, 053, 067. So these steps in time are not uniform because it was using an adaptive step size algorithm. And then if we can continue until the program is completed. And that's, this is a very simplistic way to use this library, but it works, it works well. But we noticed that we didn't specify any error criteria, so it's using some kind of default error criteria itself. If we want to numerically integrate a system and we want adaptive step size in order to control the error, we're going to have to use another integrate function and possibly supply our own explicit instance of a stepper in order to control that information. Another example they have here, this chaotic system example. Here what they've done is they've put, it's still Lorenz, but they've put, they've used different types for the state of the system and the potentially different types of the state of the system and the data structure that hold the derivative. And what they're doing here is it's a Lorenz system, but they're computing so-called Lyapunov exponents for the system. And you can see an example here where they've explicitly instantiated the runga kutta stepper, and then they're calling integrate n steps to get a bunch of transient steps iterated first, because the Lyapunov exponent for a system is a measure of its, rather than try to recall this from memory, let's just look at Lyapunov exponent. Lyapunov characteristic exponent of a dynamical system is a quantity that characterizes the exponential rate of separation of infinitesimally close trajectories. So the idea is, the higher the exponent, the quicker two trajectories diverge from each other when they start out close together. And this certainly is the case in the Lorenz system. We talked about it being a chaotic dynamical system, so initial trajectories can diverge. And the idea here is that they're going to iterate the orbit. So oftentimes the sequence of states of the system as a collection is referred to as an orbit. And so they're going to iterate the orbit initially to get rid of any transient response, and then they're going to use this Graham-Schmidt algorithm. Now this is something that's supplied with the examples. It's not part of the base library of ODEint, because Lyapunov exponents are a thing from chaotic systems. It's not necessarily a concept from numerical integration. So you can certainly steal this code. It's under the Boost license, so it's free for you to incorporate and modify and sell, etc. But it is not technically an numerical integration concept. It's a chaotic dynamical systems concept. So the idea here is that they're going to do a bunch of integration steps to get rid of any transient response at the beginning of the orbit. Then they're going to do 100 integration steps, and they're going to compute a Lyapunov exponent for the system. And then every, every 100,000 counts through this loop, they're going to print out the state of the Lyapunov exponents. So if we take a look at this one, Lyapunov exponents, you have to, as you might imagine, because of the way this one is too slow to run in debug, so let's switch over here to release. Because we're taking orbits and we are iterating them, and we are trying to identify the amount of divergence of orbits that start close together, it takes quite a bit of computation. But you can see that these Lyapunov exponents, although they are changing, they're also, it looks like the second exponent is bouncing around a lot, but the third exponent and the first one are converging down. So I don't pretend to be an expert in the mathematical analysis of chaotic dynamical systems. I just know that there's some pretty pictures that you can get out of it, and that's what I'm more interested in. I have studied it somewhat, but it's been a while since I looked at the particulars, so some of the things I'm saying may be slightly inaccurate. Forgive me. Any errors are mine and not anyone else's. Here's just an example of where they've got a custom data structure for a 3D point, and they're going to use the 3D point to represent the state of the system. And you can see here they're referencing the state variables as members of the struct rather than as indices into an array if the state vector was represented as a std vector or as a std array. You would use indices, but here they're using members of the struct. So this is just an example. It's the Lorenz system all over again, just like that first example that we looked at, but here they are using a custom data structure to hold the state and the state of the system and the derivative. Otherwise, it's pretty much the same. Now, this final example, this van der Pol stiff. Now, I did mention that in the beginning here that there's a thing called the van der Pol oscillator, which is a model of an electronic circuit. An oscillator circuit generates a repeating sine wave typically. This van der Pol oscillator is such that if you use the right combination of electrical components in the circuit, it can actually produce chaotic oscillations and not regular oscillations. Now, that's normally not what you want in an electric circuit, right? You want an oscillator that reliably produces a sine wave at a certain frequency. But as the circuit was studied further, they found that it had regions where it would exhibit chaotic behavior. Now, in mathematical terms, there's something called a Jacobian, and that is an alternate way of expressing the derivative of a set of ordinary differential equations. And again, rather than relying on my crappy memory, let's just go over here and look at a Jacobian. I think we have to go here. Jacobian matrix of the vector-valued function of several variables is the matrix of all its first-order partial derivatives. So it's another formulation of a system of ordinary differential equations. I believe there's an additional constraint that's involved in order to be able to express. Oh no, I'm sorry. I'm confusing Jacobian with Hamiltonian. Sorry. A Hamiltonian system is a way of a system of ordinary differential equations that follow a certain structure of the system itself. For instance, the bodies in the solar system can be formed as a Hamiltonian system. But the Jacobian here is just another way of representing the derivative. So when we are writing our function call operator to be used here, we're formulating the Jacobian matrix and this df/dt. So again, this third argument here is the time parameter, which in this case isn't used. But this van der Pol oscillator is an example of a stiff system. So here this Rosenbrock 4 stepper is used because it's going to, there's no comment there, but that's an appropriate stepper to use for a stiff system. So we can run this one. The output is not that exciting. Build it, release, and then we run it, and it outputted I believe this is the time, and this is the two values in the system. The van der Pol oscillator is a two-dimensional system, so that's the state vector. Am I correct on that? Let's look at the printout, see what it is. It's printing out arg2, arg1 of 0, and arg1 of 1. So I believe this is the time, or the step. Could be the, well, let's try it again. It's time, because time is going from 0 to 1,000. It just happened to be that it was going in increments of 1, so when you print it out in the general floating point format, it doesn't print out like 0.0. It just prints out the value. If it's a whole number, it just prints out the value like an integer. So it's the time and the two state variables. Now, again, if you're familiar with mathematics of all this stuff, stiff systems and so different algorithms and so on, that's going to be familiar to you. If this is your first time exploring numerical integration, you might need to go and study the specifics of the system that you're trying to integrate. In my example, in my code, I took the simplistic route. I am oh, where did I put it? Over here, I think. Okay, so for me, I am calling this iterate method, which is just going to call boost numeric odeint integrate. This is the simplistic form. I'm supplying my functor that implements either the Lorenz attractor, in this case, right, or the Rossler attractor, in this case. It's a class with a function call operator, and I'm passing that system in. My state is a 0.3, what I call a 0.3f. It's just a type alias for an array of 3 floats, and that represents the initial state of my system. Here's the beginning time that I'm going to integrate from, and the end time that I'm going to iterate to, and the delta t that I'm going to use. And my observer is going to take the state of the system that is produced at each step and throw it onto a vector. This orbit is just a vector of 3-dimensional floating point points. And then I'm going to return that orbit from this function here. And this function is called, based on whatever attractor I'm using. This is just an enum. If we go into here, this is just an enum that says what particular system I'm integrating. And so what I'm going to do in my little iterate function here, so I've got a simple struct that's got which system I'm iterating, the current state of the system, my begin and end and delta t time values, and some vector of points that represents an orbit. And what I'm going to do when I iterate is I'm going to compute a chunk of points from the current state of the system from time begin to time end at increments of dt. And if my orbit gets more than 10,000 elements, I'm going to erase a chunk off the front, and then I'm going to copy the chunk that I just got back from the integrator onto the end. I'm going to update my state so that the very last state that's computed this time around will be the initial state the next time around, and adjust my beginning and end points in time to reflect the updated state. And the rest of the code in this example is just WixWidget's code to set up an OpenGL canvas and have some menus and stuff like that give you the ability to switch which system you're iterating. So we'll build this and take a look at it. It's not necessarily exciting graphics-wise, but I'm going to say let's do the Lorenz system and start iterating. And now you can see the 2 lobes here, and I'm adjusting the transformation matrices to fit whatever the bounds of the orbit are. So it's expanding and contracting slightly as these orbits get outside. Now you can see here, this is the downside of using fixed size steps. This is, not too tight of a turn, but it's tight enough that as I took these fixed steps in time, you can see the polygonal approximation to the underlying curve. Now, if I used an adaptive step size algorithm, it might take more steps, and resulting in the same number of points in terms of points per second that it's computing, but it wouldn't have as much curve length on screen because the points would be closer together, so the length of the curve that is produced at any given time would take more points. But those are the choices that you make. I can switch over to the Rossler attractor, and as this one runs, you can see there's these points where it's in the plane, and then it pops out into the plane that's perpendicular to where this kind of circular pattern is. And again, where things are changing rapidly, you can see the polygonal approximation here, and using an adaptive step-size algorithm might be better there. Now, let's stop this and switch back over to Lorenz and run again. Now, it's a trade-off, the adaptive step size. I may have to take more points here where it is changing rapidly, but along this section where it's fairly linear, I could take larger steps. So when I use a fixed step size, I'm actually producing more points along this very linear region than I need. If I was using adaptive step size, it would figure out that the curvature is not changing very much, and so it could take larger steps, and then it would get out here where it starts to bend over again and say, aha, I have to take smaller steps, where it's bending quickly here, and then as it starts to flatten out again, it'd be like, I'm sorry, I said larger steps. It has to take smaller steps over here where it's bending more quickly, and then when it gets flat again, it can start taking larger steps again, and so on. So it's not necessarily the case that choosing adaptive step size means that I'm going to get less curve length, arc length on the screen for a given chunk of iteration. It does mean that there's going to be more computation involved, because obviously I'm having to do work to measure the error associated with my step and do extra computation to reduce or increase the step size based on the error that was produced. But as with most things in mathematics, especially when it comes to numerical integration, there's trade-offs of these different algorithms, and there's no one algorithm that is the best for all use cases. And the way you're going to use boost.odeint to suit your use case is we'll go back over here to the library, and you're going to choose your stepper in order to get the best fit for your use case. What you find out is that the actual integration, these integrate functions, equidistant observer, integrate a given number of steps, observer calls at each step, observer calls at given time points. These different functions, you see there's variations with steppers. Some of them take a stepper argument, and some of them do not. The convenience functions basically are the ones that don't. And so really the algorithm is the same. The way you're controlling the behavior is by supplying the appropriate stepper. And then, the observer is what you use to get the state of the system and the in-between points. You notice here that the signature for all these functions is it takes the system and the initial state, but if you don't supply an observer, you won't see all the intermediate points. You'll only see, at the end, after you've integrated to whatever this time value is using these time step increments. So that's basically, again, without going into too much mathematical detail, that's basically how this library works. This little example that I've written, sure, it does plot this in 3D. There's no, I'm not giving you any way to manipulate the view or rotate things around. I'm not doing anything fancy, changing the color as you go across this, as you traverse the attractor and so on. So it's extremely rudimentary visualization. But the nice part is that I didn't have to write my own integrator, this integrate library, or integrate function rather. I didn't have to write any of this stuff, and I have written it myself before using the description of the algorithms Runge 4 with adaptive step size in the famous book Numerical Recipes, which covers more than just numerical integration. It covers a whole bunch of different numerical algorithms. I have written an adaptive step size Runge 4 integrator myself by hand using the algorithms in that library. I think the edition of the book I had was it was for Pascal, and I was writing it in C. But while it's possible to do that, it is also something you need to be very careful about the implementation to make sure you're doing it correctly. It's easy to make mistakes. So I'd rather have had this library available to me when I wrote that stuff. This library didn't exist yet. This library started in 2009. When I wrote that implementation in C, I probably wrote it like 20 years before that. But the only part of this library that I was a little bit disappointed with is that the CUDA examples had suffered a little bit of bit rot, and I wasn't able to build them on my system. In particular, they were targeting, the examples were targeting SM13, which has a current smallest, I think the current smallest SM version that is supported by the CUDA 13 toolkit is 7.5. So it's been quite a while since those examples were written. And I have a feeling they're using the thrust library. So the idea was that by using the thrust library, they could use the thrust vector, which is a vector type that can be used on the GPU under CUDA, and they could use the thrust vector to hold the state and the derivative values that they were computing, because otherwise the rest of the code in the library, it's all header only, so it should just run fine on the GPU. But I think thrust has changed in the meantime, and so the current version of thrust that accompanies the CUDA toolkit has had some changes, and it didn't work quite right. So that was the only thing that was a little disappointing, is that I couldn't get these CUDA examples to work. I didn't try the OpenCL examples, so I don't know if they are suffering from a similar problem. It is, as they mention here, using arbitrary precision floating point types. It is possible to use this library with boost multi-precision. So if for whatever reason the state of your system needs more precision than can be supplied by a float or a double, and you need arbitrary precision floating point values for the state of your system, the state variables of your system, that is certainly possible. And you might think, why would you want to do that? Well, if you're exploring the divergence of orbits that are close together, in order to push that all the way to the limit, you want the orbits to be very, 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 very close together. And that means that your initial values, the initial state of your system, has to differ by some epsilon that's possibly smaller than the epsilon that can be held inside a double or a float. So you want multiple precision arithmetic in order to represent some values that differ by an extremely small amount. As I say, the documentation is good. If you're going to use this library, I would recommend reading all the way through the getting started and through the tutorial section. And then, if you need to, you can read details on the implementations of the steppers and the generation functions, the integrate functions, and so on. You can read the details of the concepts if you feel that for some reason you need to supply a custom stepper. You're going to want to read up on the stepper concepts to make sure that your implementation is conforming with the expected semantics of the template types that are used. As far as I know, they have not updated this library to use concepts, as in C++ concepts, in the C concepts got voted in C++ 23. Required part of C++ 20. So as far as I know, the library hasn't been updated to use C++ 20 concepts. So as with a lot of template libraries, if you're supplying your own custom types for the template arguments, you may get, the so-called error novel, but that's just, par for the course if you're going to go down that road. You can see that they basically got the different algorithms and adapters, each on their own headers. So, and in some of these things, runga kata cache carp 4, you may say, like, that's kind of a weird name. If we go over here, runga kata cache carp. The cache carp method is a method for solving ordinary differential equations, a member of the runga kata family of ODE solvers. So if you want to know more of the mathematical backgrounds and details of some of these algorithms, you can basically, at this point, you can, search Wikipedia, or, maybe you have to go to, the Wolfram site for Mathematica, what have you. And these, as I say, these algorithms are well known, well studied, been around for a long, long time. So it's not like it's going to be some obscure thing if you try and search for the specifics. Overall, I like this library. It was very easy to use for my little, again, this is kind of a dumb example in the sense that it's not fancy on the visuals, and I didn't even give you a way to move this around in 3 space. But I was able to put this thing, I spent more time working on the Wix widgets, GUI classes, and the OpenGL part than I actually spent on the numerical integration part. The numerical integration part was really quite easy. The rest of it was, getting all this glued together and having it work appropriately. So, nice library, easy to use. Easy to use for the simple cases, and easy to use for the more advanced cases, although we didn't apply that in my example. If I'd had more time, I would have updated my example to use adaptive step size, which is always a nice thing to get better visuals. But overall, thumbs up, and we will see you next month.